Hey guys, my name's Chris. I am going to show you how to design a low noise amplifier, 3 GHz low noise amplifier. I hope you like my video and please subscribe. So first of all, this is going to be the first video out of another video I'm going to make. The first video here is designing a more idealistic low noise amplifier using the schematic diagram, and the next video is going to be more realistic using the layout, PCB layout of the whole design, which will include all the parasitics of the circuit. So as you can see, I've already unarchived the file for ATF55143. You can get it from the Broadcom website right here. You go to documentation, or just Google it, Google this, then go to documentation and download the ADS model. You could also use the S parameter file, but for this video I'm going to show you with the ADS model. The first thing, I've already also included the schematic for the whole layout of a preamplifier. This is the representation that you would use for biasing the transistor, and you always need to use a DC block capacitor, DC feed inductors to keep AC and DC from interfering. Good thing to use these. And so another thing is that you need to include these vias here for the transistor. The transistor is an ADS model, so you have to make sure everything is correctly represented the way it's supposed to be in order to work the same way as like an S parameter file. So you go to the data sheet and you can go down to the bottom. They'll also even have the ADS model here again, but you can the better accurate ADS model is actually on the download for the ADS model. So here's the vias here, and here's the substrate. So you're going to use all of these values, put them in as I did in here. You can verify that I was correct with all the values, which I was. And now the first step is biasing the whole circuit. So to bias it, I want to bias my circuit at a voltage between the drain and the source for 3 volts, and the drain current is 30 milliamps. So I want to have the same bias point, because that will give me all the accurate information for the noise figure, and that's what's important to know for designing your low noise amplifier. So I've already included here the 3 volts for the drain to source voltage, and now you could vary the voltage here in order to get your drain current to be 30 milliamps. I've already, as you can see, I already know the value, and you can try to figure it out yourself if you wanted to. But here it is, and I'll show you that it's already shown actually. Alright, it's already shown 30 milliamps is the drain current. So the next step after biasing is making sure the whole circuit is stable at all frequencies. You want to make sure that all frequencies are stable, or else it's going to act like an oscillator. So I'm going to include shunt resistors. You can also use your resistors in your biasing network when you actually when you use the actual resistance values and everything. You could use those values. You could use those biasing to stabilize the circuit also. But since I'm just using these batteries here, you could just use one battery, and then create the biasing network and everything here. But for simplicity, I'm going to use shunt resistor here. You could also use extra transmission line here at the sources, and that's one reason why you would want to use a ADS model for your transistor, because that will make your S parameters a lot different than what they are in the in here. So the S parameters are going to be totally different, but the noise parameters are going to be the same, so you wouldn't have to worry about that. So for simplicity, I'm just going to use these shunt resistors. It's always good to have a really high value for shunt, because you don't want all the power going into your resistors. You want most of your power to go into the output and input terminations here, your 50 ohm terminations. So I'm going to put 500. It's a typical resistor value for shunts for that. So oh yeah, one thing I forgot. You need to have the stability factor palette here, and now we can look at this stability factor for all the frequencies here. So now, as you see, from 200 megahertz to 2.2 or 2 gigahertz, everything is unstable. So in order to fix that, we have to change the resistor values. We could put 300 here, we could put 300 over here. Try that. As you can see, the stability factor is really close to 1. I think you could design a circuit like this. But if you're really close to something that's between 900 megahertz and 600 megahertz, you may, if you're near a transmitter that's has a lot of power between those frequencies, your circuit may oscillate. So it's best to always have your have everything above 1. And I've already know the values already that will be best because I've already done this circuit before. And it looks good right here. But the thing is also, it's good to also look at your stability circles. Make sure those are good because you don't want to have stability circles surrounding your Smith chart. So go here, source stability circle, and then load stability circle. Just put them anywhere. And now simulate it at 3 GHz. So just, oh wait. There you go. Load stability and source stability. There. Now let's go down to about 3. This is really high value. For the chart. So here's the Smith chart right here. And here is your load stability circle here and your source stability circle. When it's not circling the Smith chart, then we're good. You know, at our frequency, it's stable. But sometimes, I'm not kidding, that your K factors are all above 1 and your stability circle can be surrounding the Smith chart. If I switch the values, if I switch these values right here, 200 and 300, so this is 300 and this is 200, it's going to surround the Smith chart, as you can see here, right? And if you look at the stability factor, ignore this. If you look at the stability factor, everything is above 1. So it looks stable to me, you know, but if somebody has a good response for this one, that would be great if you can comment on it on the video and tell me why I get a good stability factor for everything and that my stability circles sometimes could be out, like surrounding the Smith chart, which isn't good, you know. So I'm just going to go ahead and do it the way that I was doing it before. So 200 and 300, everything is done. So when that happens, I forgot 3 GHz there, 3 here. See the Smith chart. Hey, let's go to 100 points. As you can see, it's going upward, which is good because it's not going around. It's not going downward, which means it would be touching the Smith chart. So, you know, not touching, but it would be going around the Smith chart. So we're good. That's what we want. Now the next step is to optimize the design between gain and noise figure. That's the the best designing part of everything, I feel. So that step, let's put that back actually. We don't need these anymore. And now we want available gain circles and we want the noise figure circles. These circles will figure out which point our source reflection coefficient will be at. And this is actually the optimum source reflection coefficient right here for the noise. But you don't want to have optimum noise reflection, because if you get really close to that, you may lose a lot of gain, and that's not good. So that's why it's better to have your source reflection is going to be a little bit higher than what these are. So let's go ahead and I want to show you a book here. So this book taught me a lot about microwave stuff, S parameters, and how to design microwave preamplifiers. It's really informational about everything here. They have everything about it here. So this is where I learned about most of my stuff here. So so the next thing is to go to this is the last part of everything here, which shows you how to figure out what point where your source reflection coefficient is going to be. And the source reflection coefficient can be is going to depend on what your design is. So if you really want a lot of gain, then your source reflection coefficient is going to be closer to the middle of your available gain. Your circles for your available gain are going to be high gain, and it's going to be small. The circle is going to be really small, but the noise figure circles are going to be a lot bigger, meaning that it's surrounding a noise figure that's above like 2 dB maybe for this transistor. But for mine, everything's below 2 dB, even if I put a really low noise. I mean really high noise. It's not going to go less than 2. So I'm going to go ahead and put in here. So the available gain circles are always going to be larger than 10 dB. As you saw in the book here, this is 14 dB. So with mine, my available gains are going to be a lot higher for this amplifier. So I'm going to put about 16. I'm going to put 15, 16, and 17, and 18 dB. And now the noise figure circles cannot be higher. It cannot be lower than the minimum noise figure. The minimum noise figure is right here. So at 3 gigahertz for 3 volts 30 milliamps, the minimum noise figure is going to be 0.59. So that is the minimum. Cannot go lower than that. So I'm going to put 0.6, 0.7, 0.8, and 0.9. Now here's the optimum source reflection coefficient. The optimum source reflection coefficient is in polar form, but in order to put that into the function, we're going to have to put in the complex. But there might be another way of doing that. You might be able to put a function inside that function and create a complex form of it. But I'm going to use my calculator for this. And I'm going to put 0.27 and 84.7 degrees. And then change that to complex. So the complex value is 0.025 plus j times 0.269. Alright, and then the resistor value, the small resistor value is going to be 0.07. That's the normalized resistor value. And it's at 51 points. So now we'll be able to generate the noise figure circles. So as you see, the highest gain is 18 dB, but I've done this a million times, and if I go to the gain again and change 18 to maybe, let's say, 17.2, then that gain is so 17.2 is going to be the highest gain, actually. I think you could have assumed that already, actually, but I don't know. So if you do 17.1, then we got a small circle here, and we can put a point right there, which will be our source reflection coefficient, and that will be between a noise figure of 0.8 and 0.7. So let's go ahead and put our point there, because that is a good, we'll have 17.2 dB, I mean 17.1 dB. Now in order to create the input and output impedances, we're going to have the S parameters and the input, the source reflection coefficient, and that will give us all the values for the input and output impedances. And I've designed a MATLAB program that will give us the output for the input and output impedances already. You could You could use, we don't, okay. You could use functions on ADS, but the way that I do it is this way. So, okay, 0.3352. Everything looks just about the same values as I did before. I put in before. So, and this one's, yeah, this one's 46. Yeah, that's fine. Alright, and then now we need to include the source reflection coefficient, and that is 0.442 and 148.05 degrees. I got all of these equations from that same book I showed you before, and in order to obtain the input and output impedances. Here are the equations for this right here is simultaneous conjugate match, but that's usually if you get the highest gain. The highest gain would be at this point, but we're not looking for the highest gain. So we're looking to see, we're trying to optimize between noise and gain. So we have to use the equation here, the source reflection coefficient and the load reflection coefficient, and then translate that into input and output reflection coefficient, and then generate your input and output impedances from the reflection coefficients. And that's it. That's the way I did it. So I run it. Here's my input and output impedance. We don't need this anymore. And I'm going to put this over here. Now we're going to use impedance matching utility that will help us determine what impedance, what single stub matching network we can use for our design. You can also do this on a Smith chart and figure out what your values will be, but for me, using the Smith chart is going to be very tedious. So there you go. As you see, my shunts are at the ends of the closer to the output terminations. Or I mean closer to the termination, the 50 ohm terminations. So now go back to the impedance matching utility and we go to smart component. We see now we have both of our stub matches here, so I'm going to go ahead and use this one. We go to matching assistant. Our line impedance is going to be 50 ohm characteristic impedance. We're working at 3 gigahertz, and the input from here, the input's going to be 50 ohms. And now the output is going to be the input of the transistor. And the input of the transistor is going to be what is shown right here. .68 minus J times 12.02. And now you design. Now you can see that we have a open stub matching network, and open stub matching networks are prone to a lot of losses, but also you may want to use it instead because you're trying to for your design you may want a different Q factor, and that has a lot to do with it. So, and there's different designs here. There are short stubs, there are a bunch of other ones here. I forgot what kind of stub this is called. But, alright, so I'm just going to use the second one. And now I'm going to go to the second stub match on the output side of the transistor right here. This one is going to have a resistance at the output, which is the 50 ohm termination. The source impedance is going to be the complex impedance. Which is on the MATLAB 38.26 minus J times 42.85, and that's at 3 gigahertz. Okay. And again, we want shorted stub right here. And I think that's it. We're done with that. Now we're going to make the actual lengths of the line and the widths of the line. We go into the hierarchy. We see our transmission line values here. Make sure that your transmission line stub is on the end side here, not over here, you know. So from here we are going to use the line calc. That will calculate the length of the line. So my substrate is going to be 25 mil. And the characteristic impedance is 50 ohms. The effective characteristic impedance is effective dielectric constant, I mean, is 45.42 right here. And we're working at 3 gigahertz. Synthesize it. and we get so now we're going to go to our T-lines, M-line right here. We want the same configuration as it shows on the little drawing right here. So as you can see, the width is 24.53 mil. This is 195.04 mil. And this one, we have to go back into the hierarchy, change the effective dielectric constant to 164.1. That gives us a very large value. For the length is going to be really big. 704.68 mil. 24.53 mil. And over here, we do the same thing. We go into the hierarchy. Put the configuration here. Go in the hierarchy. Effective dielectric constant is 18.75. And our length is 80.5. Width is 24.53. And go back. This is a lot tedious right here. So 44.55. Synthesize that. 191. Mils. Alright. Now we replace that with our transmission lines. And don't forget that our transmission line is shorted. We need to include a short. You can also include a it's more accurate if you include a via, but for this video I am just going to show you with a ground, and that's it. In the next video I will show you how to, using the actual stub for the layout would be more of an accurate representation than what's here anyway. So let's see how everything went and see how our design went. Got a 0, 10 to 10 gigahertz. Just ignore all these warnings. They don't mean much. Alright. Let's look at our S parameter file. And as you can see, everything is at about 3 gigahertz. 17.1 dB and negative 19 dB for the S11. As you can see, this S22 is really low, and this is a really idealistic circuit. So in the EM simulation, it's definitely going to be a lot lower than that, and everything's going to be a lot lower. Even the S21 is going to be lower. So, well, this is just the idealistic one. So hopefully you like my video and please subscribe. Thank you.